Hello. Hello. How was the exam? You can remove your bag, man. Unless you want to wear it. Yeah. How was the exam? I have not looked at the questions. I have no idea. How was the exam? Good? Lengthy? Okay. Did okay? Confusion? No? Really? Gotta be something. No confusion at all. Hard to believe. Really? Questions complete? Written completely? Anything missing in the question? What? In one case, you should know that it is volume, specific volume. It's the same thing. So 1 kg. I don't think anybody needs to tell you that. That is not required. Anything else that was incomplete in the question? Okay, good. When are they going to give you the marks? Huh? When are they going to give you the marks, the papers? Not yet announced. Oh, okay. I have no idea. So welcome back. I think second half has all the appliances. Not much. Basically 4 appliances. You have the boiler. You have the compressor. You have the turbine, and then you have the condenser. That's it. You have 4 appliances. And that makes up the engine or the boiler plant. Other than that, what do you have? A little bit of control volume. You have to finish the control volume. Then you go to these appliances. That's where you will have the Carnot engine, heat pump, heat engine, little bit of efficiency business going on. And then I think entropy. That's it. That's your course. That would be your course. That's your second half. I think you're all set for entropy. I don't think I need to go through second law very extensively. I think you should know by now the difference between second law and first law. The only thing I'll focus a lot more is your appliances, where you're going to make mistakes. So I think I'll refresh your memory a little bit. In the control volume, what is constant? The volume of the system. It has a very specific boundary, and that system does not have any velocity. It does not move anywhere. It is stationary. What's moving inside is the material. So what can change in the material? The flow rates can change. So as soon as we say flow rates, there's a time concept that kicks in. So there's a time here, time. You have to think of time. So only if I say steady state process, you eliminate time. If I say steady flow process, you don't eliminate time, you say it is constant. That's the difference between steady state and steady flow. Steady state, you don't worry about time, you eliminate time. Everything's equilibrated as though you have waited for infinite time. Steady flow, it's constant with respect to time. There is a number. So what is changing is the mass flow rate. What else could be possible here? You could have multiple streams. You could have one stream coming into a material, another stream also coming into the same appliance. You could have one material going into a heat exchanger from one direction, and you could have another material making contact with the heat exchanger so that it will exchange heat between the materials. Possible, yes? Or you could have one material stream going into one blender, and you could have another material coming from another direction being mixed in the blender. So this material can simply flow with some pressure constant, while the other material can be compressed, work done on it, and then it can be pushed into your blender. So what you have to really understand here is, learn to write schematics. That's where you're going to make mistakes. You don't write schematics of the entire process, I think you're going to make mistakes. I think I gave you an example, right? There's material A coming here, and then it comes out, and then you mix material B. This is different from material A and material B mixed initially and then going into another process. Is there a difference or no? No? It's the same thing? When you read the English language, it may appear to be the same thing in the question. Is it different or is it same? It's different. So what happens is when you write the mass balance, what comes out here of material A gets mixed with material B. What happens with the energy of material A that comes here gets mixed with the energy of material B here in this location. But here what happens? They're initially mixed, and whatever else happens there, maybe a chemical reaction happens or some just physical mixing happens, and then they come out here, and then you have the total energy. So you write energy balance for both A and B here, and then depending on what process happens here, you write the energy balance when they exit. Here it's only for A, and then when the material is out, then it mixes with material B. You can lose your phone, man, later. Distracting. What else can you make mistakes with? So you have to number. You have to number like this: inlet, outlet, then 3 coming in, then 4 going out. Number it correctly. Inlet, outlet, another stream 3, or you can say 2A, 1, 2, 2A, 3. Clear? In this case, what you will write? 1, 1A, 2. Then outside here, 3. Clear? Number it correctly. What else can you make mistakes? So numbering is where you will make mistakes. What else? Pretty easy. What else will you make mistakes? Arrows. Inside, outside. Giving heat, taking heat. Doing work on the system, system doing work on the turbine outside. So you can reverse this. I can reverse this like this, and you're gone. What will happen is your left hand side and right hand side will get messed up, and your final answer will be wrong. So I'm just saying this arrow is for a material coming in. I can have heat come in, correct? Or heat go out. I can have work come in or work go out. So write the arrows correctly. If you write the arrows correctly and number it correctly, I think piece of cake. This is very, very easy. Maybe the easiest. It's fun also. It's fun for you to write the streams. I think many of your problems do have schematics. I think you should write those schematics one time and practice and learn how to number it, and then you'll get the hang of it. It's not that difficult. So what else should I recap? So steady state, steady flow. What else? You extended the energy equation, the first law, to control volume. What did you come up with? What did you come up with? Eventually, what did you come up with? You gathered everything and put it in the right hand side and left hand side, right? What did you put on the right hand side? All the inputs. On the left hand side, you put all the outputs. So what were the big global inputs? Heat and work. What was the material's flow parameters? Flow internal energy and flow work. So what did you call that as? Flow enthalpy. Yes, flow enthalpy. So you had an enthalpy at the inlet and you have an enthalpy at the outlet. And then you have the heat coming in into the system and heat going out. And then you have the work being done on the system and the system doing work on the surroundings. What else? Macroscopic potential energy and macroscopic kinetic energy. That's it. This is your recap. Anything else that I need to recap? So one more time, write the equation. Gather all the right hand side and left hand side. Put it together. I need to see both macroscopic potential energy and macroscopic kinetic energy. I'll just write one side. You write the other side. I will write the input side, which is Q dot M dot enthalpy of inlet. Write it. Why do you look at it? You've written it 100 times. Gz inlet potential, macroscopic potential energy and macroscopic kinetic energy. You can write the other side. That side will have work. Write it. Whoever is looking at the board, don't. Take your pen, open your book and start writing. There is no substitute to you working by yourself. There is no miracle. No miracle. Thermodynamics says no miracle. Clear? Pretty easy, right? You have the macroscopic component and then you have the microscopic component. Actually, you can say like you have macroscopic components, you have flow enthalpy, and then you have heat coming in, going out, or work coming in and work going out. That's it. Three boxes. That is what constitutes a dynamic control volume process. It's pretty simple. Keep it simple. So how you got Q on the input and how you got W on the, go watch the videos how you got the first law. Yes, your internal energy is like your bank balance. How much you got and how much you expended, what you're left remaining with. That's your internal energy. It's your bank balance. That's all. Clear? You cannot make mistakes with this. So why do we write summation for everything? I think I went through this last class. Because you can have multiple materials. At the inlet itself you can have multiple materials. At the exit also you can have multiple materials. So don't forget to put summation. That is why the summation is there. I think you should have the habit of putting summations because there can be multiple streams here. Multiple materials and multiple streams. Careful. I don't think you'll get any question with one material and one stream. Not going to happen. You're going to have multiple materials. And what's the energy of those materials when they come in? As usual, like your third chapter, fourth chapter, fifth chapter, temperature will be given or they will tell what quality it is. So you go to the table, you look for your enthalpy, you do all that kind of thing. Clear? So looking at the table is always going to continue till the end of your course. Otherwise you will not know what is the energy state of the material. Any other question? To clear your confusion right now. Because that's all. That's the chapter. This is the sixth chapter. After that I'm going to move into appliances. I think I did heat exchanger last time. I'm just going to recap heat exchanger and then get into other things like nozzle, diffusers, throttle, compressors, turbine. Yeah, any questions? I think I told you where mass is hidden in W and Q. Went through it last class. Go and look up in the video. Mass is there, hidden in work. It's there in work in the specific volume. It's hidden in the specific volume. density, specific volume, mass is hidden. And Q also it's hidden inside, in the area. In the area. Clear? Mass flow rate is, lose your phone, man. Did I not tell a student? Do I have to very clearly tell it? Camera should record me here. One more time. Lose your phones. Bad manners. Now am I clear? Okay. I thought I already told him. Did I not? What happened? You lost track? You trip me all the time whenever you're doing that. I don't think you want to trip me. It's distracting. You're not in a theater, you see. Even in a theater, what do they say? Shut your phones off and keep it inside. It's distracting. Some basic things. Everybody, I know you're first year students, new students. I know many people will not tell you all this. Learn some manners. Yes, phones inside. I barely take my phone out anyways in the midst of students. Barely. Rarely and barely. For a reason. I do not want to see you taking your phone out of either. I too have emergencies, you too have emergencies, but so be it. You have a family, I have a family, so be it. Now am I clear? Yes? Any other excuses you want to throw out as to why you should pull a phone out? Anybody? These are basic things. It's very basic, this is. You should pick it up in high school. Go to a heat exchanger problem. What was the heat exchanger problem that I told you? I'm going to write a schematic and you're going to solve the problem. Let's see whether you understand the schematic. Okay, here goes. Boop, 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 boop. So this is how I'm going to write. So you have to decipher this, okay? Refrigerant, that's my handwriting. Refrigerant. Vapor, VAP. Refrigerant, LIQ. What happened, guys? Very good. You can start like onion layers, peel after peel. Phase transition happened, correct? What phase transition happened? Okay, excellent. Did it give or did it take? Is it exo or endo? Very sure? 100% sure? I'm testing you after your midterm. So this is like a sort of a impromptu quiz. Exo or endo? I think some of you must have done well in the midterm. Yeah, exo. So if it's giving out heat, what should be the heat exchange? That heat should be used by who? The same material or some other material? Some other material. So I will write one stream here like this. Some other material, another material in, another material out. This side, will it be cold or hot? Is it hot to cold or cold to hot? COLD, HOT, okay, good. They make contact. It can be either by convection or conduction. We are not worried about what's the mechanism of heat transfer. Got it? So they need not physically mix, they just need to make contact, like interfacial contact. One stream can be going in one pipe, another stream can be going in another pipe. The two pipes are making very good contact, and heat exchange happens. Got it? We are not worried about how much heat goes through that steel pipe or the aluminum pipe and those kind of things. That is all completely real world. So if you get into the nuts and bolts, you also have to worry about which pipe you are using, what is the thickness of the pipe, how does the heat travel from your material after phase transition through that material and then to the other material and then to your flowing material. These are not mixing. The two flow streams are not mixing. Got it? They are in separate pipes. They are in their separate pipes. Okay, now you do this one exercise. I think this will take care of your chapter. So what did I break up your entire equation into? Heat giving in, heat taking out. Work giving in, work taken out. Flow enthalpies, macroscopic potential, macroscopic kinetic. So we'll consider this to be a steady state process. So you already wrote a steady state equation. That's how you put the input on one side and the output on the other side. Correct? You have already written a steady state equation. Clear? Because you made the entire change of dE by dt to be 0. That's how you put input on one side and the output on another side. Clear? Okay. Now I'll just read out some assumptions here. Consider potential energies to be negligible. That means the height will not change between inlets and outlets. What will you do with the macroscopic potential energy? 0. Put one big 0. Consider the velocities to be very negligible of the inlet and the exit. What will you do? Of both materials, got it? Both refrigerant and consider this to be water. Water is getting heated. Both the refrigerant and the water, the inlet and the outlet velocities, consider it to be negligible. It is adiabatic. There is no heat going out to the surroundings. This entire system is put in a box, so it is adiabatic process. What do you do with Q dot? 0. There are no moving parts, so consider work to be negligible. What happens to W dot? 0. What are you left with now? Write down the enthalpy balance. So the question would most probably be, I would have given you what is the temperature of the inlet, temperature of the outlet, temperature of the other material inlet, temperature of the other material outlet. Write it. Open your book and write it. I would have given you the mass flow rate of refrigerant. I want you to find the mass flow rate of water. How will you do it? That's the question. I've given you T refrigerant inlet, T refrigerant outlet, T water inlet, T water outlet. Refrigerant is phase changing and water is getting heated. I want you to find the mass flow rate of water. I've given you the mass flow rate of refrigerant. Write it. That's why you have to write summation. So you told the only thing that you're left with is HE equals HI, correct? But don't forget, you're multiplying it with mass. But you also have to write summation. Write the summation. Tell me what's the final equation for mass flow rate of water. I've given you mass flow rate of refrigerant. Write the equation. Doable. So this can get slowly complicated, right? You can change the potential energies, you can change the positions. Correct? You can change the positions, yes? So don't think every time you have to consider it to be negligible. I can change the velocities, yes? The inlet velocities and the outlet velocities. You have to consider the kinetic energy. That's it, there's nothing. You have written the balance, right? Input, output. Depending on your assumptions, you make zeros, and wherever there's no zeros, you ask for the values. Yes. That's where the heat transfer is happening between them. Yeah. Mm. Don't say decreases, it's isothermal phase transition. Refrigerant is just changing its phase. Absolutely. Hmm? Correct. 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 Which, so second section is cold again. So again it meets another section of refrigerant. The transfer happens and then it moves again. So we are not saying that it is stationary, it is moving, but the velocities are low. So you don't have to worry about inlet kinetic energy and exit kinetic energy. They are the same, they are very slow and they remain to be the same. I am not doing any kind of acceleration of the material inside. Got it? Yeah, it cannot be stationary. If you are stationary, you are done. You're finished. It's over. That's all. The process will be incomplete. Got it? Then we don't have any heat exchange at all. There's no point in heat exchange. That's why this is a continuous process. So for heat exchange, so what he's talking about is like a batch process. Is it good to do batch process for heat exchange or a continuous process? Huh? Batch process is cumbersome. Yeah, every time you put a block of ice, you cool something, take it out, replace it again, put a, not a good way of doing it. So it has to be a continuous process. So it is moving, but it's moving at a very low velocity and there is no change in velocity. Yes? There is no change in velocity. Anything else? If the positions change, you have to change the potential energy. Clear? So it won't be as simple as this. This is a very simplified version of heat exchange. What else can I make it can I have here to make it more complicated, more real world? Good, you brought that up, batch process. What else can I have here? Can I put in some work for no reason? Yeah, let's say after my material gets heated up, I will have some surroundings do work on the system to make it more compressed, to increase the pressure. Can I do that? I can put a work here and ask you to find what happens here at the outlet. So when you do work, I can also say I increase the pressure and I also increase the velocity of your exit heated water. Now what you will do? The exit kinetic energy, you have to ask me for the number, I will give you the number. The velocity increased to blah blah blah, I'll give you the number. Yes? Got it? I can give you the mass flow rate, I can give you T1, T2, T3, T4, I can tell you how much work is done, I can ask you find the velocity at the exit after work has been done on the heated water. That's also possible, yes? Cool off on the heat capacity. If you start going with heat capacity changing, then it's real world, complete real world. Density will change, heat capacity will change. I think I told you this in the last class, we are not making it fully real world, got it? Then my enthalpy will change, my velocities will change with time, my positions will change, everything will change. Internal energy also will change with time. We are not going to that part. Again, thank you, that is the real world. If you really want to do modeling, you have to plug in all that. The heat capacity, internal energy also will change with time as soon as it gets heated. So that's why we are calling this as a steady state process, like as though you waited for a very long time and then you did your numerical. Got it? So when we do steady state heat exchange in the mechanical department or civil engineering department, we don't consider the changes of heat capacity with time. So that's why the guys will heat the copper rod and then they will they will chat on their phone outside and then they come back after 1 hour and then take the temperature reading at different locations. You know what I'm talking about. They wait for steady state and then they do it. So, but as you know, that is not it's time consuming. So the answer to that question is we have a dynamic thermal conductivity probe in the mechanical engineering department where you will measure thermal conductivity in less than 2 minutes and you also take heat capacity changes into consideration. How about that? It's called a dynamic thermal conductivity measurement. Doable. It's pretty accurate. No principle. You have to do calibration and take care of the heat capacity change. You just use the unsteady state equation. Now you just made it steady state, right? You use the unsteady state equation. And you solve for it numerically, there's a solution for it. But we don't do any numerical solutions in the experiment. What we do is we get the real numbers. Change in temperature, interfacial temperature, you're talking about water and refrigerant coming and making contact, right? So we actually measure the interfacial temperature changing with respect to time with the real instrument for 2 minutes. And then from the slope, I can tell you how the change, whether the kappa is high or kappa is low. But it's not just kappa, there is Cp also there, correct? So I do some calibration and get rid of the Cp change. So I will give you a thermal conductivity, right? Exactly what you're talking about. We bring both in contact and we measure the interfacial temperature change with respect to root of time because that's the solution for the unsteady state. Yeah, you can go to the mechanical engineering. I forget which lab, sorry. So good, this is good, clear? Okay, one more example before we call it split. Who has heard of the word nozzle? Yeah, come on, you cannot say no though. All of you take shower, right? Okay. Shower heads. Shower heads. Played around with shower heads. If you go to the hardware store, you will see different types of shower heads. Shower head. Got it? What is the big deal about that? Because there is a lot of money spent on its design. I'm not kidding. There's a whole lot of chemical engineering and mechanical engineering that goes into design of all these shower heads. If you don't believe me, go look it up. Incredible amount of money is spent on it for design. What's the big deal? The man is an environmentalist, went directly to water conservation. As honorable as your thought is, I wish the design guys also think like that. I don't think they think like that right at the beginning. I think their thought process goes a little bit more different. Huh? Your friends will, you're complicating it to your friends if you use words like viscous forces and all that. You tell them in a much more simpler, natural language. If you minimize, once again, if you minimize viscous forces, what are you doing? What's the opposite of it? Exactly, very good. Use the raw language, free movement. What is free movement? What happens to the jet? Velocity is more. You thin it and you increase the velocity of the stream. This is not exactly about water conservation finally comes into it, but there is a velocity increase by the designers that they have in their mind. Why is that? Huh? Why do they want velocity increase? Otherwise, why will you have shower heads that give you mist? You know, there's all kinds of settings. There is spray, there is mist, there is Niagara Falls. I'm not kidding. Am I? Go to the hardware or check into a 5-star or a 7-star hotel. I think you'll see it. You'll see the settings right there. I am not kidding. It's got falls, it's got mist, it's got your regular spray. By the way, you get such kind of jets when you see it. Come on, give me a shot. What's the reason? With a certain velocity so that they can clean your body. Yeah, and that's where the conservation comes. Got it? So effective cleaning leads to less water. So eventually that's, but also to give you that feel of that you're under the, the Niagara Falls. The nice natural bathing experience. So how is this possible? The design guys are doing what? Because the flow is coming from your regular pipe, cylindrical pipe. What are they doing with the shower edge? They're changing the area as well as the dimension, the shape and the area. So they're constricting it or they're diffusing it? Constricting it. Very good. So what happens when you constrict? Because the flow rate will not change. The same flow rate, you have the pressure gradient in the main pipe, you open the valve, whoosh, it will shoot out with the same flow rate. What you're doing is you're changing the area. So to compensate for the change in area, what happens? Velocity will increase. So these holes or these shower heads are called nozzles. It's like you're squeezing the fluid. Got it? You're squeezing the fluid and pushing it faster. You're increasing its velocity. Any other application other than shower edge? Shower head is my example. You give me another. Oh, very good. Oh, nice. So you for car cleaning, huh? Okay, so what do you do with your finger? Okay. Excellent. So it's your own nozzle that you have created. Yeah. And that created a jet which is going faster, correct? Any other example? So you want fast velocity into your throat. Maybe not advisable. So, have you seen plastic parts? All these parts? These are all injection molded. So these are very viscous materials. When the plastic is melted, it's very, very, very viscous. So how do you get all these intricate shapes? Buttons. I'm just giving you a simple example. Button itself is a very intricate shape. So button will be small cavities sitting there. So how does this viscous melt actually go uniformly and fill these button cavities or pin cavities or other very intricate plastic parts that you have seen, pens, pen handles? So without squeezing, will it go in and resolve and take the shape? You have to squeeze it. So they go through nozzles. So you literally squeeze the melt. So since you said viscous, these are extremely viscous. These are high molecular weight materials. So these are viscous. So the only way to make them flow uniformly with a good amount of velocity is to pinch them, squeeze them. How do you squeeze them? Send them through a nozzle. So one small caution you should use, the area change should be gradual. Yes? If you keep it sudden, what will happen? The jet will not have time to adjust to the area changes. Got it? It will go hit the boundary and it will get accumulated and start rotating right there. It will lose its energy. So all your design, the edges and the corners, you have to keep gradual changes in dimensions for a reason. Otherwise, you will have stress concentration there. You'll have stress concentration. That's why if you see most of the designs, you will have a curvature there. Nobody should have a sharp corner. So you're riding a bike. What if I give you a sharp left bend? No, you're going to go hit the wall. Obviously, yes. Get it? You have to have a gradual change. It's the same thing. You're moving. You're like a fluid. You're moving like a fluid. You need to give gradual changes in area as well as directions. Otherwise, it will hit the wall and it will get accumulated there. So, inlet to outlet, you will have area changes. So I said squeezing. Now can you write the picture of the nozzle with the stream? So I wrote one opening here. This is a pipe. So now help me. I said squeezing. and gradual area changes. How should I go? Some fancy design like this? Okay. Can you write and label your inlet and your exit? And write VL, however you want to write, velocity inlet, velocity exit. Where will the velocity be more? You write it V velocity exit greater than velocity inlet. Nozzle. Now go to steady state process. So now they will give you a numerical now saying that after it comes out from the heat exchanger, the same fluid will go through a nozzle, blah blah blah, at some velocity, and it will come out at another velocity. Now, and this is a steady state process. So what assumptions will you make here? There is no significant heat transfer. Take off Q. There is no moving parts. There is no work done. Take off W. One second. Let's not go to the, hold on to the potential energy. There's no significant heat transfer. Q is gone. There's no significant work done. There's no moving parts. W gone. There is no positional change that much. Ignore potential energy. What are you left with? Kinetic, tell me correctly, macroscopic kinetic energy and what else? Microscopic kinetic energy and enthalpies. You're left with enthalpies. Yes, you're left with enthalpies. You're left with enthalpies. Got it? I did not say ignore enthalpies. So now, one last question, because it's the question hour. So I'm bombarding a saturated vapor from this side, and I want to increase its velocity. So it's coming at some pressure inlet, some temperature inlet, and some velocity inlet of a material, and it's in the saturated, sorry, it's in the supersaturated, superheated vapor. I'll just say P exit, and say P exit is less than, what could have happened? Obviously, man, it's here to here. We just spoke now, squeezing the liquid. Oh, by the way, should I ask again, what's the direction? Left to right? From your viewpoint, or right to left? Okay. Boo, boo. Tell me what happened. I gave you enough data here. I gave you enough data. If you want, I'll give you the velocity of the exit also. But conceptually, tell me what happened. Superheated guy is coming and getting squeezed into the nozzle through a gradual change in cross-sectional area, and its velocity increased. The mass flow rate remains the same. What could have happened? I gave you one hint though. I put a PE and I gave you the PE is less than PI. It's your call. What could have happened? So what happens when you give restriction? What happens to the pressure? You said velocity increases, completely agree. What happens to the pressure? Huh? No, that's why you should not talk like a plumber. Sorry, the plumber says pressure kam ho gaya. Actually what he means is pressure gradient has decreased. So you have a driving force for the liquid that's coming in here with a delta P. When it hits a restriction, does the delta P remain the same or does the delta P go down? Because delta P is between the pressure that's at the initial state and where it's coming, its destination. That is delta P at which it's coming. When you give a restriction, did the delta P increase or delta P decrease? Did the driving force increase or driving force decrease? It's already coming with a pressure. If you put a restriction, pressure also goes up. So what happens to delta P? Decreases. Delta P decreases. The pressure gradient decreases. So what usually the plumber says? Pressure kam ho gaya. When there is clogging, he says pressure kam ho gaya. Got it? What he means to say is pressure gradient went down. So there's a delta P coming from your valve, main valve. And when it hits a restriction, it accumulates pressure here. So what happens to delta P? Goes down. So it's not just about the velocity going down. What happens to the pressure gradient? Goes down. Now you know where I'm getting to this hint that I've given you. P exit is lower than P inlet. So you're losing pressure, yes? You're losing pressure gradient. So what is happening to that superheated vapor that's coming in and hits a little bit of geometric changes? Its gradient begins to decrease. So when its gradient begins to decrease, its flow work is beginning to increase or decrease? Flow work is decreasing because its ability to do work is decreasing, correct? What is flow work? P multiplied by velocity V, yes? That's the flow work, P multiplied by velocity, clear? Flow work, flow work. So the flow work decreases, yes? So now, would it have to do more work to do the exit work? Because it decreased? Yes, it has to do more. So what happened? It did a lot of work and it lost its pressure. So what happened to a vapor which does a lot of work? It loses its energy, it loses its pressure. What happens to it? It becomes two-phase. Possible it might become two-phase. Got it? A nicely compressed, hot, superheated vapor hits a block and its pressure gradient goes down and its entire inlet work starts to decrease, so that now it has to do, if there was no change, what would have happened? Inlet work would be the same as exit work. So it becomes what? Mostly it becomes a two-phase thing. So the enthalpy will come down or enthalpy will go up? Come down. Yes, internal energy will come down. Catch you tomorrow.